So, good morning, everyone. It's a really rainy day here in Sweden. I hope you're having better weather than us. Today, from RISE, it's Fernando Huerta, me, Jenny Adrian Meredith, Anna Stenebyr, and Sara Lundqvist who's hosting this meeting. And we would like you to mute your microphones and turn off your videos. The seminar will be recorded, and both the presentation and the recording will be available afterwards. And Fernando, who will be doing the major presentation, he likes questions during the seminar. So write them in the chat box and we will address them during the seminar. And then we will also gather questions and have them in the ending and have a discussion. So I will introduce RISE a bit, and then Fernando will talk about AI in retrosynthesis. And then, as I said, questions and discussions afterwards. And as you know, maybe, RISE stands for Research Institutes of Sweden. And before, we used to have a lot of research institutes in Sweden, but a couple of years back, 30 research institutes went together to form one research institute, and we are more than 2,800 employees currently, and we work all over Sweden in a lot of different fields such as agriculture, pharmaceuticals, bioeconomy, materials, and much more. And this breakfast seminar has the background in a team that are addressing challenges for digital questions within process development. And we have a background in chemical process and pharmaceutical development as Anna, Fernando, and I, but we also work together with sensor systems within RISE and applied digitalization. And we have, this is the second breakfast seminar in this series that we are arranging. And today you will meet Fernando Huerta, and I will tell you a little bit about his background. Fernando took his PhD in Spain at the University of Alicante, and then he came to Stockholm University to do his postdoc. He went back to Spain for a short time, a couple of years, before he decided to come to Sweden and work at AstraZeneca in the beginning of the 2000s. He stayed with AstraZeneca until 2012, and during this period he was involved in the team for the evaluation of different synthesis planning software packages. And in particular, he became part of the AC team collaborating with Infochem in Germany and develop the development of IC-Synth. And after finishing at Astra, he formed Chemnotica with two former colleagues. And they worked a lot with research prediction. And in 2016, he joined RISE, and he has been working with us since, and he's working with synthesis, but he's very involved in AI, machine learning, and prediction using tools. And you feel free to contact us at any time, and we will have both Fernando's and our contact information at the end of the seminar. So Fernando, feel free to take over. I will.
Thank you. I'm going to try to share my screen. Yes, I just need a minute. And here we... I hope all of you see me.
Yes.
Thank you, Jenny, and good morning. I hope you have better weather than we have here. It's not the perfect fall day, but you know, just take a cup of coffee and enjoy the talk. Retrosynthetic analysis. Yeah, this is this is an important topic and a very old one. Even before retrosynthetic analysis was studied as an own subject, synthesis, organic synthesis was already going on. Maybe you remember, if you've been studying chemistry, you remember what was the first ever molecule synthesized in the lab. I think most of you know that. I think it's urea was the first one, but what was the second? That's important. Let me see if I can make now. Wait, I'm in the middle. Sorry, I will move up. Yeah, the first one was urea, was back in 1828. That was a long time ago, almost 200 years. And yeah, was organic molecule, but hey, just one carbon. It took many years later to put two carbons in a molecule, and it was in 1845 when acetic acid was first synthesized. And still in the 19th century, we have the aspirin. Acetyl salicylic acid was synthesized in the lab, and but it took quite a lot of time before retrosynthetic analysis was studied as an own subject. And at this point, I just want to mention that maybe you're going to be disappointed, but I'm not going to talk about all the technical aspects of retrosynthetic analysis. So forget about the strategies or hear about symptoms, retrons, transforms, all that kind of thing. Instead, we're going to discuss more philosophical matters, and then we will see how we have advanced in this topic over the years. At this point, I would like to bring back a very old debate regarding retrosynthetic analysis. And this debate, there was two groups, and in one of them we had these two guys. I don't know if you recognize them. One of them is Robert Woodward, and the other one is Alexander Todd. Both are Nobel Prize winners for different synthetic accomplishments. I mean, Woodward, for me, particularly, is the father of organic synthesis. Come on, this guy synthesized B12 back on the days when NMR was using 60 megahertz, things like that. It was amazing. But these two guys, they agree in something, and they stated back in the 1960s, something like that, that organic synthesis was an art, that there was not possible that a machine or computer could mimic the logic and intuition of a chemist when planning and designing a synthesis. Opposite to these two guys, there was this other guy saying that, well, you can recognize him. He's Elias James Corey. He's the only one that is alive nowadays, and Nobel Prize winner as well. And I think he stated back in 1969, if I'm not wrong, that he said something like, and I quote literally, that soon computers will plan and design synthesis better and faster than humans. Yeah, this is a very, very old debate, and it's very difficult to, take part of one of those who was right. That is almost impossible, and we are not here to discuss that today. But what we can do, if we are going to talk about retrosynthetic analysis at this point, is to introduce the star of the presentation. And if you have to agree with me, if we talk about retrosynthetic analysis, the absolute and wonderful star of this presentation is the target molecule. Without target molecule, we don't have retrosynthetic analysis. Well, this is our target molecule for today. It's a biased indole. It's a natural product that, as far as I know, has not been used for any particular reason. It's just a natural product. But it's going to be very useful for me during this presentation. So if we try to update that old debate, when we are going to do a retrosynthetic analysis, what we are going to do? Are we going to look at modern methods? Or on the other hand, we are going to use traditional approach? Again, nowadays, we don't know what is best. it's very difficult to take a side. Most likely we have a compromise between the two. But what we can do now is to check how is this done today. Imagine that you in your companies or your chemist or your favorite CMO, you ask them, can you do an analysis on this molecule to find ways to synthesize this molecule? Well, you have to be pretty sure that the first thing they are going to do, they are going to put that molecule in SciFinder or in Reaxys or in any other reaction database to see what has been done. If the people in charge of doing this analysis, they have the knowledge and the resources, they can even use one of the modern computer-assisted aided synthesis design software that they are available. Here you have a list, there are many more. So I just took some of them and just pointing out the one at the bottom in green, they are open source, so everyone can use them. The rest, they are commercially available, so you have to pay for using them. And as Jenny said, I've been working in the past and for many years with the development of IC-Synth. And I was very lucky to be one of the first ones trying Chem Planner. At that time, it was called ARChem. And well, anyway, if you do this and you did analysis using all the modern technology that we have in our hands, and you understand what is behind the back end, what is the algorithm, the engine, you should know that the analysis of you're going to make is going to be based on rules, on templates, on fingerprints, or even a combination of those. What I want to say is that the retrosynthetic analysis is going to be based on similarity with respect to rules, with respect to templates or fingerprints, whatever. And bear with me, if it's going to be similarity, the ultimate comparison between our molecule and what is down out there is quite easy to understand that out-of-the-box solutions are going to be very difficult to find. And I can agree now that maybe, just maybe you don't, I will put myself away. Maybe you don't believe me. So at this point, I want to do an experiment. Let's try to do the retrosynthetic analysis of this molecule here live, so without net. If we do this for real, you will ask your experts how we make this molecule. And I think almost 99.9% of all experts in chemistry, they will suggest this disconnection. This is the most logical disconnection to make this molecule. So we will end up with two starting materials looking like the ones here. We have two separate indoors with appropriate X and Y functional groups that we can couple together somehow to make the final molecule. Okay, when we have these experts' opinions, we go and we try again. Let's see SciFinder or any other reaction database. And when you put your idea and your molecule here, what you find is, here we go, one hit. It is possible, what we suggest. We always do like this. We have an idea and we go and check for our idea. In this case, we see that there is one example, is two indoles moieties, a boronic acid in one of them. And okay, guys, I mean, we all think that we are better than we see. So we see here 55%, we can do better, isn't it? It's always like that. Anyway, that's great. So, but we want to please our bosses and say, now we have to do something else. So we go and we use one of the modern computer assisted methods that are out there. So now that we are in SciFinder, SciFinder has the possibility to use Chem Planner. So we put the molecule and ask Chem Planner to give us options. If we do so, there we go, we get exactly the same disconnection. I marked them here in red dots. So Chem Planner suggests exactly the same disconnection. That's not difficult to understand since Chem Planner use SciFinder as source of knowledge. Okay, this is like when we go to the doctors, you always want a second opinion. Let's try something else. Let's try ISIS Finder. That is an open source tool we can use nowadays. And here you get exactly the same disconnection. And that's looking quite good. But okay, we are not satisfied. We want to do something else. And we can look for ASCOS, that is another open source possibility we have. And again, we get the same disconnection. So at this time, what we can say is that absolutely all modern methods and everything, what they do is to validate experts' opinions. And bear with me, this is wonderful. This is great, actually. I remember 10 years ago, a computer could not match, do the atom mapping in a simple Diels-Alder reaction. So, you know, when you have your diene and your olefin, your final product, and then find where is the diene part, what is the olefin part in the final product, a computer could not do that. So the fact that now we have systems that they can actually validate experts, I think is absolutely wonderful. Nevertheless, if this task is on my desk, that my boss asked me to do this, for me, the question now is very obvious. Is that it? What I do now? My boss asked me to make a retrosynthetic analysis of this. I gathered together all the experts. We agree in this disconnection. SciFinder, ChemPlanner, ISIS Finder, ASCOS validate this disconnection. And now what? I write a nice report to our customer and say, hey, look, we have done this and that and that. And this is the best. Wait a second, it's not the best. It's the only solution we have found. It doesn't seem right, isn't it? It's not 100% right. So I want to show you what we do at RISE and how we approach these kind of situations. At RISE, we have a method to do this analysis, and I'm gonna try to explain it here. It's not fully developed, so please understand, this is just a presentation. I'm not gonna put all the details, but more or less you will get an idea. What we do at RISE is we look for all available transformations that exist to make all bonds that we can disconnect in our target molecule. We disconnect those bonds using synthetic logic. What I mean is, for instance, the bond between the 6 and the 5-member ring is not going to be disconnected because that is illogic. But we look for all possible transformations to make all the bonds that they are marked here. You have, I think there are 6 examples, but we look for even more than this, just to see what is out there that can help us. Furthermore, we don't use substructure. We use a graph of the target molecule, in this case, a subgraph. And the goal is to find all transformations within the network of organic reactions. I mean, in the first round of searches, we don't care if to make this bond in between the 2 indoles, if you have a nitrogen or oxygen or a sulfur on the other part of the molecule. It doesn't really matter. We will analyze those data afterwards. So we do this for all bonds. And then when we have found and gathered all the information, what we normally do is we present different synthetic alternatives to our customers. Here is an example. Normally we come up with 3, 4. For this presentation, I'm gonna put just 2 of them. So here you have the 2 alternatives that we found, among others. The synthesis alternative 2 that you can see here on your right is the expert disconnection. You have the boronic ester in this case and a bromide, and then you make this bond, compound number 18. And but we found another one, and synthesis alternative 1 makes another different approach. Actually makes 2 bonds in one simple synthetic step. This reaction is Laroque indole synthesis is called, if you want to know it. And anyway, what happened next is that when we write down all the alternatives, we look for all the different reactions to make each step. So we do generic searches for all of the steps. And please don't look at the number of steps and say, okay, this one is 5, this one is 6 steps, this is better. No, because they are protection, deprotection steps, so they are not counted here. So don't look at that at this moment. So when we have all that information for all the searches, we do data mining, and we do all of this in a semi-automatic process. At the same time, we generate quite nice, I would say, tables that we can show to our customers and take a decision in which one they want to try. Just to show you a few things that we look at very early on in this process. These are some of the parameters that we are looking at, and some of them, of course, availability of starting materials, electronics, like compatibility of functional groups, molecular descriptors, fingerprints, of course. Then something that is important for us to validate and to give robustness to our suggestions is the number of different transformations to make one particular bond. Just think you want to make, I don't know, a carbon-carbon bond. There are many different ways to do that. I mean, you can use transition metals, you can use lithium, you can use magnesium, Grignards, and that's the kind of chemistry we are looking for, because give us some certainty that it's going to work. Then for almost all our suggestions, or when you try to do something new, there's going to be some steps that are going to be more speculative than others. For those steps, we can create models to predict if they are viable or not. And since, as Jenny said at the beginning, we are a department that will look at the end for process chemistry, we start looking at the select criteria very early on in this process. And I said, this is just a few of the things that we look at very early on, and we have many other things to look at. I mentioned that all of this is done in a semi-automatic process, and just for your information, we use KNIME as an analytical platform to do data mining, and the models are written in Python. Here is an example, just few screenshots from what is KNIME workflow, the Python, and this is here on the right. You have an example of these comprehensive summaries. So I don't think this correspond actually with the synthesis at hand, but anyway, it's just for you to know. Okay, now we have everything. Now we have suggest how we do, or how we plan the reaction, and this is all theory. Now we need to put the theory in practice. We go from computer to the lab, and at this stage we need to find what's the best way to run, in this case, this Laroque reaction. Normally, from the beginning, we have our experience and the structure of the reaction we want to run, but then what we do is compare that with the reaction databases. We check what is out there, what is the knowledge around this transformation, and in the intersection between these two is where we find the suitable reaction conditions. In this particular case, where you have, this is a palladium catalyzed reaction, the amount of potential reaction conditions can go up to 100. I mean, you have to combine a palladium catalyst, a ligand, base, solvent, and additive. This reaction actually works best when you have lithium chloride present. So the combination of all those variables, they can end up with 100 different reactions. And you know, our customers, they don't come to us and pay us to run 99 failed reactions to just find the one. That's not nice. We cannot go there and say, yeah, we are going to try 100 times. We know we are going to fail 99, but we will find it. So what we do we use data mining and molecular descriptors to limit the amount of possible reaction conditions. By doing this, well, of course, we are more cost efficient, and we generate less waste. I know these reactions are all in a small scale, but at the end of the day, there are many reactions that you have to throw away. Of course, we increase the successful outcome, and I will add that we increase the happiness of the chemists doing this work in the lab, because that's also important, I think. Well, now you know how we plan and how we translate our theory from the computer to the lab. I've been mentioning that we use models, and let me show you in the next slides a little bit of our interest in this area, which are our research areas of interest in machine learning and artificial intelligence. One of the first things we do is we are looking for models to predict reactivity, and understand me, reactivity in this case means yield. As you can see here, we have two examples, an amide coupling and ester hydrolysis. And well, we have pretty good trend in our models. So that is, but of course, we need to work much more on this. We are developing now these models as we speak. Another area of interest is to use machine learning to help us in the selection of the right transformation. Let me explain this. Imagine you have this target molecule, this thiophenol here. It's not a thiophenol, it's thiophene, number 1 here. And you find that, okay, the disconnection we want to make is this one in between the, the side chain. But when you look at this in SciFinder or any other reaction database, you find out that there are many different possibilities to do that bond. As a chemist, we are biased by our experience. So if I've been working all my life with organozinc compounds, obviously I will try to do this target molecule using this approach down here with the number 9, number 8, or the other organozinc combination is number 3, number 2. And probably it's not the best, but this is the ones that make us feel more comfortable. So what we want is to create models to help us to identify which one of these are the best. As I mentioned before, we also have models, and we work trying to predict reaction conditions, or at least to limit the amount of variables in a single transformation. And finally, the other area of interest, but this is quite related to the first one, is to find out chemo and regioselective reactions and models to predict. I mean, you have an aniline and you want to do a halogenation of the ring, you can predict, depending which regions you're going to use, if your iodo compound is going to, or halogen compound is going to end up in ortho, in para, or in both. And well, we are not the only ones in the world doing this kind of work. There are many other groups. I mean, the amount of publications within this area has been increasing exponentially in the last years. And if I'm going to give you now just a parenthesis here, and I would like to speak a little bit about what is the state of the art in all this process, how we are regarding using machine learning and artificial intelligence in synthesis. And allowed me to use a metaphor. And for that, I'm going to use a really old citation from ancient Rome. And I hope all of you have heard this. Let's take this quote: all roads lead to Rome. And meaning, consider that this is synthetic routes, and this is our target molecule, more or less. Something funny, and outside this context, when I was looking for a metaphor for explaining the situation, the state of the art of artificial intelligence, I thought this was a good one. So I started looking for the sentence in Google, and it's quite funny because I saw this quotation, many blogs in many websites, all of them related to this picture, and the same title, All Roads Lead to Rome. Well, spoiler alert, this is Paris. Anyway, that was off topic. If we consider that this is our target molecule, and we compare with how was the situation back in the time, back when Corey, Woodward, and Todd were discussing what was better, we can make the same comparison. This comparison, we can say that at that time they were driving a Fiat 500. They didn't know, they knew all the roads, but they didn't know the fastest way. So they were just, driving around to find their ways. It has been very, very long time until we found that nowadays we can use medium-sized SUVs with GPS, that is important, that can direct us to our target molecule. And that's what we are now. Now we have systems that they can help us to identify the fastest way and the better way to get to Rome, if I follow the metaphor. Well, what is the future? Well, the future, we are far from it, but the future will be to do nothing, to let the car drive ourselves. So I have to say we are very far away from that. But this was my metaphor of what is the state of the art and how we have been from the time when Corey and the others were doing synthesis until nowadays, and what is the future. It's going to take some time to reach this stage. Just going back to the topic and summarizing what I was saying today, I think at RISE, when we do retrosynthetic analysis, we cover more of the network of organic reactions. We try not to miss any reaction. We have in-house tools that help us with decision making, take this route or this other, and all this is communicated to our customers. We normally find out-of-the-box synthetic solutions, and please, this is good, but sometimes out of the box is not the best solution. But it's important, even for patent purposes, that we find all possible solutions, even though bad ones. And just coming back to the first debate about how it is retrosynthetic analysis, if it's an art or is science, I would say that we combine both traditional and modern approaches. But, combining art and science, we were not the first ones. Thank you. I will stop sharing now.
Yes, thank you very much, Fernando. I will share my screen since I have some contact information as well. Let me see. So it's time for some questions. Did we pick up any questions from the audience? Otherwise, I have a question, or I have a couple of questions. Fernando, how do we cover the possibilities? I mean, this is a broad and large question, but I mean, there is a vision and you work with this a lot. And in your opinion, how do we cover the possibilities that are within AI and digitalization? Would you like to?
Well, I think in our situation, our current situation in our department and within the RISE consortium, we have, honestly, we have a unique disposition because we work synthetic specialists with some knowledge in data mining and computer science with actual artificial intelligence specialists that they work in another department, but they help us. So we come up with the problems with our way of thinking as a chemist, and they help us. I think some of them, they were here. Johan is here. they help us to identify, there is one, identifying which algorithms, which data process you should do to make this happening. So I think we have a unique, I've been talking to a lot of people that they do models for chemistry, but they are data scientists. They miss our point of view. So I think we have a unique situation at RISE.
Yeah, I completely agree. You're using descriptors. Is there other descriptors that that you see that can be used in the future or currently?
We are fighting with this approach. I mean, if you understand how we do the process, and it's in a simplistic way, let's say that we take a reaction and we find out data. The data for the reaction is the descriptors for each part or each component of this reaction. And that amount of data, it has to correlate with the reaction mechanism. And if you are the one listeners have studied chemistry, there are many factors. There are kinetic factors, there are thermodynamic, there are transition states, there are catalysts that they favor one reaction or other. So all that life, for me, is life. You know, a reaction is something that is alive, that we have to interpret the data. So I don't think we have enough descriptors nowadays to cover all the reactions and to understand all the reactions. But we are working with that. We are working, okay, which kind of transformations can we work with the descriptor we have? Then someone else or ourselves, we will come up with new descriptors eventually. But this is a process that takes time. So we will see.
See, yeah, the future will tell. Do we have more questions?
It was crystal clear.
It was crystal clear now, but I can discuss this a bit more. So what do you see? I mean, when and you talked about this a bit, but communication, can you elaborate a bit about communication? Because you will get results that are quite broad and
yeah. That is one part. I missed it during the talk. It's very important when as I presented, we come up with a lot of synthetic alternatives. Here for the presentation, I had only 2, but normally there are 3 or 4. Our customers, they are the ones, they have been struggling with the problem, of the synthetic problem, longer than us. So they can orientate us and say, no, that step does not work. So that synthetic alternative that we suggested is not valid because, and in this aspect, what I have seen, and I've been working with RISE just 5 years, but my experience says that an open communication in terms of knowledge about the problem is what it makes a difference. It makes our life easier because we suggest things that they didn't try. So we don't have to spend, waste time things that they have tried before and they know they didn't work. And it helps us to find more because, but that is something, now we have potential customers here, and this is not politically correct to say, but I have seen many times that to share knowledge is difficult. People are afraid to share too much knowledge or too little, or to say, no, we are not good enough, or we are better than you. No, this is excitement. This is about finding something that is new, and we have to do it together. So I think it's one part of the success of our retrosynthetic analysis and our ideas is to establish a very good communication with our customers and share all the knowledge we have.
I agree, and we are closing into the end of the seminar, and I'm how and we would like to invite all our everyone who's interested to continue the discussion with us. And how do we maybe you can discuss talk a little bit about this. How would I act if I wanted to come in contact with the RISE and discuss a bit more in depth, and maybe also start projects together with us?
I mean, the first step is to, of course, you must have a problem in synthesis. Otherwise, well, there is other part of RISE that can help you. But if you want our help, is just tell us our synthetic problem and contact us via you, Jenny, or any of the available possibilities, or email me directly. I mean, and we write a NDA and we take it from there, and we can show what we can do. This kind of a work, not as extent as I have presented today, but just a first analysis. I think we include it in our quotations. So don't be afraid to ask us to look at your molecules and come up with ideas, because just as a part of that, when we make a quotation, we used to include our first findings. So, and then we take it from there. I love to discuss chemistry. So,
yes, but an NDA is very good to start, and also we can have introduction discussions with you, quite no strings attached. But we are happy to talk furthermore with all of you if you're interested in this field that has a lot to offer. And here are our mail addresses, but you can also find us at risere.se if you want to phone us straight away. So before we stop, I think 45 is a perfect time to stop. There's still some. Yes, 1 second. Yes, Fernando.
You have seen the question, I guess.
I didn't see a question because I'm sharing my screen.
Well, there is a question saying, people intrigued by models building with data, to show more some light on that. Okay. I'm not an expert in data, as you say that, I understand. But what in this case, our models, I don't know how to explain it. Imagine that you have a reaction, and you have your starting material A plus B to give the molecule or the product C. You calculate this. I mean, you can write the reaction with the structure, with ChemDraw or any program that is out there. That reaction, we calculate properties for each component. We calculate the descriptors from the starting material A, the B, and the C. And then you get a number of descriptors. So this data for each component of your reaction. If you put that together, you generate a matrix. It's a matrix of the reaction. And that matrix tends to be unique. So even if you do a small variation in one of the molecules, there will be some changes in the descriptors. So you generate a new matrix. And that's how we work with data. We use the reaction matrix, we call it, but I didn't want to get into too much details today. But in another occasion, we can discuss how we do these things. And well, we can ask Johan and Eric, that is not here, that they are our experts in data, and they can explain much more, much better than I do, how random forest works. Random forest finds correlation between that data, but it takes not the whole table, it takes parts of the table and find correlations. So that's the way of doing it. I hope it was a little bit more clear than before.
Were there any more? Yeah, there's something else in the chat.
No, it was just a thank you.
Okay, thank you. Okay, But then let's wrap this up, and feel free to contact Fernando or Anna or me if you're interested in discussing this further, or if there are any question that pops up, you're most welcome. And we will have more breakfast seminars during the fall. We haven't booked them yet, but there will be, you will be invited by as customers to us, but also via LinkedIn. We will invite you. And we will probably talk a bit about green chemistry further down the road. We hope that that's what we're planning up next. Okay, so hope you get a great day today and not too many meetings, I hope. Thank you.
Thank you. Bye. Bye,
Bye.
everyone.